Although the title is specific on TOPCon crystalline silicon solar cells, I would like to talk a little bit about some general topics like solar energy and solar cell technologies, and then I will move to our recent research topics like local TOPCon structures and a kind of new or not a kind of hybrid new structure for bottom cell for tandem applications. And finally, if I have time, I think I have half an hour to talk. I will talk about a little bit manufacturing in Turkey because it is also becoming a kind of attractive topic for the PV industry in global sense. Okay, well, let me start with this slide. So the solar electricity is becoming cheaper and cheaper, as you all know. So when you look at the levelized cost of electricity, we see that the PV electricity is the cheapest one today, which the graph shown here is for Germany, of course, but this is even better for Morocco and Turkey because we have more sunshine and we have probably cheaper COE value. So it is the cheapest one, and of course with the climate change issues and several agreements, also some national economical reasons, now the installation in the world is increasing. Now today it has reached more than 2 terawatt peak installation worldwide. Of course, here China is the leading country in both in the production and in the installation. So we see a lot of tenders in recent years and a lot of installation all around the world. Well, I want to show you this picture. It's from our country, from Turkey. This is a huge power station located in the middle of Turkey. It's 1.2 gigawatt DC power station, a single station, which is one of the maybe largest in Europe. And of course, there are many others in China bigger than this one, but this one is quite representative for our region. So there are more than 3 million PV modules used in this facility. So it's really impressive. The length of the power station is about 20 kilometers, they say. Well, okay, as you all know, maybe I just briefly and quickly summarize the solar energy technologies. We have two systems. One is called concentrated solar power, CSP, and the other one is based on photovoltaic systems. In the case of CSP, we generate steam by concentrating the solar radiation onto some pipes or on the top of a tower. Then this steam is then used to generate electricity by using standard turbines. Well, in the case of PV, of course, we have photovoltaic devices which converts the electricity directly from sunshine into the system. And photovoltaic system is, of course, much flexible. It can be very small and it can be very large. So large power stations can be made, or very small applications can also be found by CPV. And of course, due to the also price advantage, CSP has lost the race against the PV technologies in recent years now in terms of the electricity generation. So today, PV system is dominating the electricity generation industry from solar radiation. Well, as I have already mentioned, the total installation in the world has exceeded 2 terawatt. In Turkey, we have a little bit more than 20 gigawatt installation in our country, and this is rapidly increasing now. Well, when we look at the photovoltaic solar cell technologies, we can classify them as four major technologies: crystalline silicon solar cells, thin film solar cells, multi-junction 3-5 solar cells, and of course, new devices, new structures, new materials. So when we look at the market share, crystalline silicon solar cell technology is dominating the market with a more than 95% market share, but thin film is declining. I mean, is becoming less and less now. Today, its market share is less than 5%. When we look at the standard energy generation applications, we do not see any market share for these multi-junction solar cells made by using 3-5 semiconducting materials. In the case of perovskite and organic PV, well, the market share is quite small, and perovskite is of course very promising, but still there are issues like stability and also large area manufacturing, etc. But we will very soon, I think, soon their market share will increase with the new technological development. So let's look at the crystalline silicon solar cell technologies. That some time ago, about 10 years ago, the dominating technology was so-called aluminum BASF solar cell technology. In here, we have P-type silicon substrate. On top of that, we have N region, which creates PN junction here. And then on top of that, we have silicon nitride and also metallization. So on the backside, we have aluminum coverage fully on the backside. And during the processing, some of the aluminum diffuses into the substrate, creating a P+ layer on the backside, which provides the electric field effect, which is useful to reduce the recombination on the backside. So the maximum achievable efficiency was about 20% with this structure. But later on, of course, new technologies have been developed. The most successful one was PERC, the solar cell. In this case, the backside of the solar cell is no longer in touch fully with the aluminum metal layer. Instead, there are some local touch here, some local contact between aluminum and the silicon substrate. So the other regions are covered with the passivating material like aluminum oxide or silicon nitride. So this local contact structure on the backside has improved efficiency enormously. So we have seen efficiency values around 24% by using this PERC cells. Well, the industrial production is still going on, but the total, I mean, average efficiency is around 23%. But it seems that PERC technology is disappearing quickly after the success of TOPCon type of solar cells. But of course, IBC, interdictated back contact solar cells, is a very promising, very nice approach in which the PN junctions are formed on the backside, and the front side has no metal grid, metal connection, which reduces the reflection from the front surface, so which gives us a higher efficiency. Now today, still, I will talk about this later on, but today this type of solar cell structure is still on the market and is gaining also share, increasing its share with some new development in China. Well, of course, the other alternative is heterojunction solar cells, which is also very good, I mean, very high performing solar cell structure, which combines the thin film technology with the crystalline technology. So instead of having a junction into silicon, we have amorphous silicon on both sides, in this technology, which provides the electric field required, needed for the charge separation and collection. Okay, well, you see the efficiency values in IBC and heterojunction. 27% have already been reached, and they are still, I mean, being improved by R&D studies all around the world. Well, one of the very successful approaches in recent years has been TOPCon type of solar cells. In here, the backside is totally isolated from the aluminum layer, so there is no direct contact between metal and the substrate. Instead, we have a very tiny silicon dioxide layer, which is the blue one here, and on top of that we have a polysilicon layer. So this polysilicon layer provides the necessary electric field on the backside or junction to separate the charge carriers and reduce the recombination. So when we remove the contact between metal and the silicon here, we obtain an excellent passivation on the backside. So then the efficiency has reached about 26%. At the industrial level, the efficiency is around 25.3 or so. I mean, the Chinese companies are now producing with such an efficiency value. But of course, another difference here is the N-type use of N-type substrate instead of P-type, so which also provides a higher quality in terms of carrier lifetime. So today, TOPCon share is really increasing in the market very quickly, and all investments in Turkey in the coming years will be based on TOPCon, probably, most probably. Well, what will happen after this? So it's a question, of course. A lot of people are working on tandem solar cells using heterojunction structure, but we are expecting this TOPCon route to move into into different directions. One of them will be TOPCon Tandem. The efficiency will be more than 30%, of course. And the other one is IBC TOPCon structures, which is already realized. I mean, you can find a commercial product using this technology today. Also, another maybe option can be P-type TOPCon, so making P-type, making TOPCon solar cells on P-type substrate. So we can have either high efficiency or cost effectiveness in this case. So all industry people are, of course, discussing this, what will happen next. So these can be the options according to our evaluation, our judgment. Well, what are we doing at GÜNAM? GÜNAM is I will later on give you very short information about our research center. We have created a quite extensive, comprehensive infrastructure to develop solar cells in Turkey. At the moment, we are focusing on TOPCon solar cells because of the industrial relevance. So far, we have studied the tunnel oxide, which is needed on the backside, this thermal silicon oxide. We have studied phosphorus doping on the backside. We obtained excellent passivations, and boron diffused emitter on the front side has been quite well produced and also passivated using aluminum oxide and nitride. So we have developed our own hydrogenation experiments for this structure. And as a new concept, and maybe for the future of the technology, we are looking at two major structures. One of them is the local TOPCon structure, local TOPCon structure on silicon. The other one is the bottom cell for tandem application. So for tandem applications, we are developing a specific TOPCon PERC-like solar cell. I will come to that point later. So I mean, these are just some experiments showing the passivation quality we have reached so far. So we have looked at different polysilicon layer on the backside, and we have reached extremely nice, good passivation values. As you can see here, the implied VOC values have been, have been like close to 750 millivolt, which is the one of the highest maybe in the existing literature. So the recombination current density on the backside will be as low as 1.5 femtoampere per centimeter square. So these values are really very promising. But of course, reducing the polysilicon thickness is an important issue to reduce the parasitic absorption on the backside. So this is also something that we are studying, and you can look at this paper if you like to know more about this. Well, local TOPCon is an idea to reduce the recombination losses on the front side. So backside is same as the standard TOPCon solar cell, but on the front side we have another TOPCon structure under the metal layer, but outside the metal layer we do not have any high doping, heavy doping. So the emitter is lightly doped, but the region under the metal layer is passivated by using a poly layer, and then we have a very good, very low front side absorption. So this is the idea. So here you can see more details on the right side here. So we have a local P plus TOPCon structure under the metal, but rest of the emitter region is not covered with any poly layer, of course. And this is so-called local TOPCon structure. Well, here, of course, you have a very important patterning problem. You need to pattern the poly layer on the front side. So this is something that we have studied. Well, doping has been optimized, and we have very nicely optimized the front, front surface doping. I mean the doping the poly layer, and we have developed some new recipes for this by including some pre-annealing steps, etc. So this is already published. So if you are interested, just let me know. I can send you the paper. So here with this poly TOPCon layer on the front side, P poly layer on the front side, we have reached quite high implied VOC values and low recombination current values. Okay, how do we pattern the front side poly layer? So to do this, we have first produced the poly layer on the front side, and then we have printed somehow. I will come to that point. We have printed the boron ink on locally here, which provides high doping. And then after annealing, we etched back the remaining part, because heavy P doping provides a quite high resistance to the potassium hydroxide etching. So this is not etched away during the etching process, but the rest of the emitter region is etched away. So in this way, we have been able to pattern the surface. Well, this fine line printing has been done together with Fraunhofer ISE, and this paper is published, by the way, in Progress in Photovoltaics. In here, the boron ink is printed by using a technique called flex rail. The more details can be found in these papers here. So we have been able to make fine line printing by using this flex rail technique. So it provides a high printing speed and also very consistent and variable finger width, so we can control the finger width very nicely. So you see some pictures here, and we can have printing down to 24 micrometers. This can be even reduced, but we haven't tried that yet. So different finger width can be obtained in this way on planar and textured wafers. So what happens to the passivation on the backside? So we have seen an excellent passivation properties in this case. The average IVOC values of 720 millivolt has been obtained, and also the J0 values or the saturation current values below 100 femtoampere per centimeter squares have been obtained. So ongoing experiment, we are, doing more experiments to integrate this structure into a working solar cell. Well, another topic we are focusing on is the bottom cell, which is very, attractive and promising as far as we see. In this case, the cell structure is shown here, up here. Backside is very much like a PERC cell, but the front side is different. On the front side, we have a polylayer, polysilicon layer, and the TOPCon structure. So this, on top of this TOPCon structure, we use aluminum doped zinc oxide for the recombination junction for the perovskite top solar cell. Here you see the fabrication steps. I'm not going to explain all the details, but we have a well-known, well-established backside technology and good passivation as today, because PERC cells is well known, and this system, this structure is very well, compatible with the high temperature processes and also with the industrial production. So in this structure, we have measured the open circuit voltage at one sun. So we have obtained VOC values up to 700 millivolt. Of course, it gives us a indium-free and silver-free structure for the tandem fabrication. So as a recombination junction on top, we are proposing to use aluminum doped zinc oxide. The transparency of azo layer is very good. So this is showing the transparency measurement, transmission measurement, but more interestingly, the implied open circuit voltage values is extremely high, very good values we have obtained, and up to 750 millivolt has been reached. So it is showing the promising future of this structure for the tandem applications. So these experiments have been performed under the project activities Nexus, which is funded by European Commission. Well, let me just give you some information about the center that we are working in. We are in Ankara, of course, you probably know that, and we are part of the university. We were part of the university until 2021. The university is the Middle East Technical University. It is one of the leading technical schools in Turkey. GÜNAM is located here in the campus, a nice region with a lot of green and forest around. Our center has been organized as 6 divisions: silicon PV, emerging PV, module technologies, power electronics, concentrated solar power, test and characterization are our main divisions. We have more than under 20 people working in the center in these divisions. Okay, we are running many projects, so I'm not going to explain all of them, but currently we are part of 14 Horizon Europe projects, which is a successful performance for our center in our country. So here are some pictures from the facilities that we have. These facilities belong to Silicon PV. This is a pilot production line for crystalline silicon solar cells. Currently, we are upgrading it to larger wafer sizes, which will be more compatible with the industrial research. So I will quickly go through the other divisions. So the emerging PV is working on perovskites, organic PV, Tandem, etc. And the ModTech division is working on module technologies and also outdoor testing, also PV integration like agrivoltaic, BIPV, VIPV. These are all their focus points in their research activities. Powering Europe is working on powering, I mean on power electronics. They develop new inverters and new architectures for the circuits used in the inverters. This concentrated solar power technologies division is working on concentrated solar power, but they are focusing on not on the electricity generation, but they are focusing on heat generation and the use of this heat in the industrial processes, and test and characterization is another division which is serving both our research groups as well as the industry. Well, let me just go quickly to the PV manufacturing in Turkey, or the new official name is Turkey. In Turkey right now, we have too many module makers. It's very popular now in Turkey to make modules. And there is one integrated ingot wafer cell and module factory, Kalyon PV. It's in Ankara, close to us. They have a capacity 1.2 gigawatt. CW Energy is a company in Antalya, in the south coast of Turkey. They are now building first TOPCon line in Turkey. The capacity will be 1.2 gigawatt. Smart Energy is ramping up a PERC line in the city of Izmir. They are actually producing now, PERC cells. And several new cell manufacturers are also on the way. Okay, also the components manufacturers are also existing in the country. Okay, well, I just mentioned that there are too many module makers, so we have counted 71, but somebody says there are more than this value. However, the total capacity of these lines are about 35-40 gigawatt per year. However, the total annual installation is only 3 to 4 gigawatt per year. So we don't know exactly what will happen to these companies, because some of them will disappear because they cannot export their product to Europe because of the Chinese competition. Well, Turkey is a favorite site for PV production because, first of all, the cost of production is quite attractive. We are close to Europe, but the cost of production in Turkey is like India. This is one advantage. So the labor cost is quite low compared to European companies. Energy cost is low. Another point is that the energy generated in Turkey, used in Turkey, mostly coming from, I mean, the 40% of the energy generation is provided by renewable energy. So it gives us a very good position in terms of carbon footprint. So and this is increasing. So we will be, producing with much less carbon footprint than many other countries. So it's also making Turkey as an attractive country for PV fabrication. So these are some pictures from the existing companies. This is Kalyon PV. They have ingot production, they have wafer production, cell production, and module production. And CW Energies in Antalya, they will start very soon. They are almost ready to produce TOPCon cells. All machineries are from China, by the way. And Smart Energy is also in Izmir. They have already started production. And finally, I would like to mention that Silicon PV will be in Ankara next year in April. So you are all welcome to attend Silicon PV 2026 in Ankara. So I think that's all I want to talk about today. Thank you very much for your attention. Any question, I will be very happy to answer.
Thank you.